We are back again with another video, and in this video, we are going to have an overview about the modern CPU architecture. So without further ado, let's get into it. A CPU is basically the brain of a computer. The CPU is the center of everything in the computer and handles all the computations needed to turn inputs from memory into outputs on your peripherals. CPUs are general purpose, flexible architecture that take in a stream of instructions from all types of workloads and computes or process information based on those instructions. Let's have this brief history. ENIAC, which stood for Electronic Numerical Integrator and Computer, the first general-purpose digital computer from 1946 that were about the size of a house and that was built using vacuum tube technology, now fits on a chip inside your laptop, which we now call a microprocessor. This ability to continue shrinking in transistors is based on a famous law that we in the industry refer to as Moore's Law. It is based on the observed trend showing that we can double the number of transistors per unit area about every 2 years. All thanks to the man behind that idea, Gordon E. Moore. Technically, the goal of CPU architecture is to make a design that is simple and easy to understand. That was made possible by John von Neumann with his 4-step instruction cycle, fetching instructions from memory, decoding the instructions, executing the instructions, and storing the results back in the memory. This has been the holy grail in today's computing industry. Noyce and Moore teamed up founding Intel and found a niche in making of memory chips, resulting to the first ever Intel 4004 processor that is made of 2,300 transistors and has 740 kHz clock speed. Further advancement led to the x86 instruction set architecture, which became the foundation of today's CPU designs. For computers to function, we represent all control and data and numbers in simple on or off states. The characters and numbers humans use to communicate with can be easily translated into binary-based system of numbers which computers can understand. Instruction layer is the chaining of functional blocks together that allows for even more complex logical functions. With them, we can build custom execution units that perform specific calculations. The ISA plays an important role as it dictates how instructions are being processed. The design and the microarchitecture depends upon the type of instruction set being implemented on the processor. The term used on the 4-step instruction cycle is called the pipeline. Using the pipeline, it enables the processor to have a better work efficiency. It also directly proportional to the clock speed, wherein the higher the clock speed, the faster and more efficient it becomes. Over time, the average number of pipeline stages has grown. In general, the more pipeline stages you have, the faster each stage can run, and more stages are being done in parallel. The more stages are added, the less is done in each individual stages. Next, branches are instructions that are like forks in the road. When executing these branches, we stop before to make sure it goes the right way, thus making the process slower. As its pipeline progresses, the number of branches increases, thus making the guessing more unreliable. To solve this, engineers devised branch predictions and speculative execution. The front end of the microprocessor contains fetch and decode stage branch predictions. They are so advanced that made them almost clairvoyant. These predictions are stored in caches. These are little memory storages with faster clock speed to optimize the process of routing back to the main memory. The main goal of the front end is to have enough and ready instructions for the back end to execute to avoid idle time. Multiple and fused UOPs are also helpful in simplifying the data that is coming out from the decoders, making it easy to execute and store in the memory. Decoded UOPs are then being fed to the back end of the CPU. The scheduler then analyzes these instructions to see if there is a dependency of instructions going on. Dependent instructions will have to wait, while other instructions without any dependency will go straight to the superscalar vector ALUs by executing them out of order. The dependency is still considered until the retirement to get the correct results. Superscalar and out-of-order execution is a huge help in the back end to help process thousands of instructions and get expected results quickly. That is all. Bye.